multiple groups, analysis of variance, and the concept, and the details are not important, I guess. The concept was, actually the concept is summarized nicely in this. Yeah, so just to recap, since it's been a while. So basically, if we have, let's say, 4 groups, doesn't matter, I picked this from some book. And we're testing the null hypothesis that the mean of this bunch of numbers, these numbers, are they different? Or basically, more precisely, the null hypothesis that there's no difference in the mean. Are we rejecting the null hypothesis or failing to reject? So the analysis of variance, basically the crux of the whole analysis is, so if you look at this mean here, this point, this point, this point, this point, there is a variability of the mean. That means if you just look at these 4 numbers as a bunch of means, as numbers, they vary. There's a variability in them. They're not identical, but there's some variability, right? Just like if I give you a bunch of numbers, and those numbers have some mean and some variability. Variability is best way to define variability is the variance. So difference from the mean squared sum and divided by n minus 1, the number of them. So that's some index of variable, how much it varies in that bunch of numbers. So if you treat these means as a bunch of numbers, in this case of course 4 numbers, there is some variability there, correct? That variability in comparison to the intrinsic data variability. That means within each group, this is supposedly same group, same animals, whatever. But for some reason, all those numbers are not right on top of each other. There is some variability that's biological, what have you. Right? So that's the key. How much is the variability across this? So coming back to the statistical word, they call it between group variability. It means how they're changing versus within group variability. So you can easily feel that if between group variability is large compared to within group, there is a very good chance there is some real difference, right? If it is not, and that's the crux. That's what variance. So it is analyzing variance of the means. It is between groups, as compared to variance within. That's the basic biological variability. That's it. That's the gist of it. The rest is all details. So this is what we say. So we had. So this is what we had done. So you can see the variability. So if you are mathematically inclined, you can see this terms here in this. This is variability of anything. So this between. Between, that means between means. So we have m means, m groups. So each group has a mean. It's the overall mean of everything, all those bunch of means. Difference squared sum divided by m minus 1, the number. So this is the variability of the means. Same exact concept. What is between group? So this is the group J, group I has a mean, individual data points of that group, summed over all the points in that group. Squared exactly same way, a bunch of numbers within the group, sum, and then this sum is repeated. This is n minus 1, that group's, I'm assuming n is the number of samples in each group, same number, it doesn't happen. And then summed over all groups. So this is the variability within, and then sort of f basically is the ratio of the two variables. So you can see if the ratio is very high, you have a good chance that is really a difference. And that's the f statistic, the ratio that follows an f curve. That's why it's called f statistics. And that curve is sort of given by, this is the f curve looks like this. So it's not that important how that F curve comes, what's the equation of the F curve, is that really not important. But you can see that if that F value is very high, so that means between relatively is high compared to within, that means that distance, the means that are separated, they are indeed separate. And that's what you should look it up. That's the concept. So all it is variability between groups as compared to variability within group. That's all it is. And within group simply is representing some biological variation that exists. Okay, so that's what we've done. So now I had just sort of, just for completeness, it turns out the t-test that we normally do, if there are only two groups, is nothing different than f-test. It's a mathematical equivalence, and those are inclined. So t-test, basically what is, same idea here, so, but it's not sure that it's this is, oops, this should have been 1 and 2. I believe. So difference in the only two groups mean and its standard deviation of that difference. So it's trying to get an idea about is that mean any different? That difference is statistically different. You just go through the steps and it's not that really, you can go through and show. It turns out if you do an f-test, because nobody's going to stop you to do the ANOVA for two groups, you can still do it and you'll get an f value. And it's really fun to see if you do a t-test, an f value, mathematically the f is t squared. It's exactly same. So it's identical. So f-test is nothing, t-test is nothing more than f-test, of course, is squared for two groups. It's really no difference. So same idea applies. T-test, there's no fundamental difference in the idea. It's still the variability. It just happens to be just two groups. So there's no difference really. There's t-test and ANOVA, no difference. You just think of ANOVA as generalized version of a t-test. You got more than two groups. So the question being asked is the same. Null hypothesis is exactly the same. There is no difference in the means of these X groups or I groups. If you have two groups, it's two groups. So
I don't know whether we brought this question up or not last time. So let's say you tested 5 groups, okay?
Yeah.
So control and 4 different kind of treatments. Yeah. And if we just did a t-test between control group number, control and experimental group 1, as if you didn't do the other 3 treatment groups, you saw a difference. When you did ANOVA with the post hoc, then you failed to see a difference, right? So what is, if you're trying to report a study,
so
but you're only
maybe this is probably what they'll answer. If not, we'll just continue that discussion.
No, it's more of a philosophical question.
Yeah, that probably sets up this thing. And the map, if you really want a punchline answer, is there is statistics not going to give you an answer. You just have to sort of answer that based on, let's just do it based on what you feel. At the end of the day, you might say it's a self-fulfilling prophecy. You will just choose what you want it to be published. Yes, there's nothing.
Let's say you write a paper, you're only reporting the first 2.
Yeah, so there's, let's say there were 4 groups. A control and a mutated group, right? Today you did a mutated group and you only knew based on the current knowledge, there was no reason for you to do an experiment except for this one mutation. I'm just making up a story. And you got a nice difference, that's done. Maybe tomorrow you figured out that there are other mutations of relevance, and you start mutating the other ones, in the same protein. So, and the question now is your experiment and the reporting that you need to do, is it all those 3 mutations simultaneously with wild type, or I'll just do wild type with 1 mutation?
Yeah, but if I did the same experiment, all 4 mutant.
Yeah, no, but what I'm saying is
at the same time, and then probably let's just say I'm not seeing the difference between 1 and 2, which I would have seen if I did the t-test.
Right. So that's what I'm trying to say is that how can statistics help? I don't see how statistics is going to help you here at all. You have to decide whether considering all those 4 groups makes biological sense to you. Is there a reason, that you want to sort of put it all together? If it doesn't, then why would I say I had 4 different experiments I did? I'm producing 4 papers. So, well, I don't know. Whatever. This is what I'm saying. A good example would be Steve is doing an experiment that he first did some. Let's just summarize here. Here's a troponin ion, and then phosphorylation status of troponin ion. What does it do to the contraction? Okay, so he had wild type, and then one he calls it pKa mutant, where the sites, a phosphorylation site, pKa phosphorylation, are mutated so they cannot be phosphorylated. So serines were made alum. Okay, that was this mouse we had first, and he did the experiment. There was some nice data coming out, whatever the end result was, it was showing something. But then subsequently, so this is upon getting rid of native phosphorylation, basically what is happening. Then we created another mouse a little later on while this was going on, where actually he calls it TGE. Where did the name come from? This name you started using. But anyway, this is glutamic acid. This is constitutive phosphorylated, right? So the expectation was that maybe, in a sense, this results would be opposite to this results, right? And now when he was getting some nice, consistent statistical data here, right? And then he put that. Well, there's another further complication here at low sarcomere length, high sarcomere, but that doesn't matter. When he puts this in, now you got an analysis of variance. If you put those, it's got 3 groups now. So this was just going along nicely with t-test and all of that. Some of the differences you saw there sort of disappeared.
Yeah.
When he put the 3rd one in here, that it's just not making the statistical significance.
Yeah.
So what do you do? No, I don't know. We haven't published.
What would you do, Steve?
So
we're still discussing.